Hello everyone, I'm Wenting Dai. Thank you for watching our paper presentation. Our paper is about self-supervised pairing image clustering and its application in cyber manufacturing. Here is the outline of today's presentation. First, I will introduce the background of big data analytics in cyber manufacturing, and then move to our topic, image clustering and its literature review. Afterwards, the proposed self-supervised pairing image clustering will be presented, followed by performance evaluation and the final conclusion. As we all know, in cyber manufacturing, translating data from the interconnected system into predictive and prospective operations often relied on the capability of big data analytics. It should make the decision based on the discovery of the hidden patterns or unknown correlations of large amounts of data. However, getting the labels for a large amount of data is time-consuming and even cannot be easily accessible due to the requirement of specialized knowledge and skills. Therefore, more and more unsupervised learning algorithms had been applied for data analytics in cyber manufacturing. Here, we focused on a basic unsupervised learning direction, image clustering, in our work. It separates images into different clusters so that the images in each cluster will provide similar visual content. And all this method can be categorized into three different branches, which are conventional clustering, low-dimensional feature representation combined with conventional clustering, and deep clustering. Although there are many proposed clustering methods, it's still challenging to achieve a high-level performance. Next, I will review this method one by one. The first one is conventional clustering, including partitional clustering, hierarchical clustering, and so on. However, their performance largely relied on the accuracy of distance measurements, which will be impacted by the cruise of high dimensionality of images. For reducing the dimensionality of images, both mathematical procedure and unsupervised feature encoding are proposed. For mathematical data transformation, such as principal component analysis, they will inevitably lose part of information, and as a result, some discriminative feature may not be learned. For unsupervised feature encoding, the feature encoder is only trained once. It means it's hard to improve further. From the success of deep learning, a new direction, deep clustering, was emerging, which learns deep data representation and clustering jointly. Specifically, in the forward pass, the input images are extracted by the representation network, and then they are clustered based on certain algorithms. Afterwards, different with previous methods, the clustering result will be used to estimate the pseudo labels or distribution for the input. For example, if the probability of an input image belonging to cluster 4 is higher than other clusters, the estimation function will assign cluster 4 as a pseudo label to this input. Then, the deep clustering algorithm will backpropagate the loss between the predictions and the pseudo labels to fine-tune the deep feature representation network. This loop will repeat until the algorithm reaches the stopping criteria. However, their limitation is obvious. We know this kind of estimation is not accurate especially for the dataset with a large number of classes. Therefore, we propose a novel deep clustering approach which learns the clustering from binary pair classification. First, let me introduce how does human learn clustering from sample pairs. Taking the first figure as an example, there are two classes, and the correlation between these 3 points are sample 1 and sample 2 from a similar pair, and sample 2 is different from sample 3. We know the sample of a similar pair should belong to same cluster, and different pair samples should in different clusters. Based on this rule, we can easily get the result like that. And the clustering result for 3 clusters and 4 clusters can also be achieved in the same way. At the same time, we can find that with the increasing of the number of samples, the problem will become more and more complicated. The next question is, how should handle an extremely complicated case, k clusters in n samples? The solution is neural network, because it's great at learning knowledge from a large amount of complicated data. Ideally, in our network, the input should be image pairs, and at the end, it will output the clustering predictions for input images. Therefore, we choose a classic pair classification network, the Siamese network, which is supervised neural network that learns data representation from image pairs. From this figure, it can be found that it consists of 2 identical subnetworks, which compute the feature vector for the input images and calculate their similarity based on the extract feature by some common similarity measurements, such as Euclidean distance. Then, it will update the network parameter by backpropagating the loss between the actual pair label and the calculated similarity. For producing the clustering prediction, we extend the architecture of the classic network by stacking an additional softmax layer that predicts the class probability for input at the top of this network. And the similarity of image pair is measured based on their class probability. As a result, training this network only requires image pairs and their pair labels, and the clustering prediction can also be produced as an intermediate result in this end-to-end network. The next step is to estimate pair labels by a self-supervised pairing module. Comparing with other existing deep clustering methods, we replace the estimating target from the class label or distribution by pair labels, which only can be positive for similar pair and negative for dissimilar pair. They are much easier to estimate than other multiple class labels. For example, in random prediction, the probability of a correct class prediction for one sample is 1 over k, where k is the number of classes. For our binary labels, the correct probability is 50%, but for more types of label, the probability will be lower, and that's the reason why pair labels are much easier to estimate. Before introducing the self-supervised pairing module, let we analyze the pair distribution in a dataset. For example, in the uniform multi-class dataset, there are k classes with n samples for each classes. After calculation, it can be found that the distribution of pairs intrinsically biased towards negative. And for this dataset, the number of negative pair is k minus 1 times f as the positive pair. Therefore, different strategy should be proposed for different pairs. For negative pairs, we propose to use the basic thresholding method. Since the angle between any two probability vector belongs to 0 to half of pi, we choose the middle value as the threshold. It means if the angle between two probability vectors larger than a quarter of pi, we treat this pair as dissimilar. As we mentioned, the pair distribution biased towards negative, so the correct estimation rate for negative pair should be good even without any training. For example, in mini dataset, the initial correct rate is 90%, and for CFR10 100 dataset, the correct rate almost be 99%. For positive pair, we know the scale is small, and the correct rate for thresholding estimation is very lower at the beginning. So, we form the positive pair by augmenting images by some FN transformation, such as flexion, rotation, and zoom in, zoom out, like the figure shows. Then, the created pairs will be used to fine-tune the representation network in the backwards part. Same as the original semis network, the pair classification loss is used. It assumes the calculated similarity of the image pair should close to its pair label. Besides, for ensuring a sensitive solution, two additional constraints are also adopted. It first requires the overall cluster's distribution should close to real data distribution, such as uniform distribution. And this loss is defined by the KL divergency. Secondly, the individual prediction for image should be unambiguous, which means it should have a dominant predicted class, like the chart of example 2 shows. And the overall loss function is get by combining these three types of loss. Here, the whole working flow is shown in this figure. In the training stage, we calculate the similarity matrix for a bunch of unlabeled images by our pairing classification network first. And then, based on the self-supervised pairing module, we create both negative and positive pairs at the same time and use them to train this network. In testing process, the clustering result will be directly provided by the softmax layer in our network. Next, in the performance evaluation, two manufacturing datasets were used. They are texture surface dataset, which shown in the first column in this figure, and the still surface defect dataset, the second column of this figure. Besides, we also evaluate the performance on several general object datasets for testing its generalization capability. including MNIST, AugMini-GLOAT, CFR10, and CFR100 dataset. And the details of all datasets are listed in this table. In our experiment, 3 popular clustering evaluation metrics are used to measure the performance, which are normalized motor information, adjusted rank index, and unsupervised clustering accuracy. They are all range from 0 to 1, and a higher value shows a better result. We compared the performance of the proposed method with all 3 types of clustering approaches. And from this table, it can be found that our method outperforms other benchmarks in the first dataset and achieved 100% accuracy in the second dataset. At the same time, most of deep clustering algorithms, including DEC, IMSET, and our method, not surprisingly, achieve better results than the other 2 types of clustering method. The same trend is also indicated in the comparison result on other general objects datasets, which are shown in this figure. The results marked by star are except from the reported papers, while others are get by running the release code. Our method also outperforms most of benchmarks except IMSET on MNIST dataset. Regarding the second dataset, our performance worked outstandingly than others. Similarly, our performance on CFR10 and CFR100 dataset is better than that of state-of-art method. For visualizing the result, we also conduct the principal component analysis on the extracted features in different epochs and choose the first 2 principal components for visualization. In these 2 figures, different color corresponding to different class labels, and we can find that with the training of the network, samples gradually become discriminative in their latent space. In order to evaluate the effect of image augmentation for positive pairs, we conduct the experiment in which all positive pairs are formed by identical images without image augmentations. In this figure, the first row shows the original positive pairs and second row shows the positive pairs without image augmentation. And the results are listed in this table, and we can find the result without image augmentation are all worse than the original method, especially in MNIST and AugMini-GLOAT dataset. It mainly because the inter-class variation in these 2 datasets is caused by the different writing styles, such as different thickness, and the image augmentation method, such as small degree of shifting, zooming, and rotation, are still able to imitate the different writing style in these 2 datasets. However, for the last 2 datasets, the inter-class variations are much more diverse, which cannot be fulfilled by current image augmentation method. As a result, their boosted performance by image augmentation cannot compare with the performance in MNIST and AugMini-GLOAT datasets. To investigate the contribution of the applied constraint in the loss function, we perform experiments of the proposed method with 3 different variations. The first one excludes all constraint in its objective function, and the remaining 2 incorporate the pair classification loss with label distribution constraint and the uncertainty constraint respectively. This table shows the result. Note that these 3 variants didn't reach the original performance in all datasets. Even the first variant does not work in a mini-globe and CFA100 datasets at all. And actually, their performance was increased normally as the original method at the beginning. However, it was gradually impacted by the trivial solution until the model failed if without any regularization. It is probably because the number of classes in mini-globe and CFA100 dataset are much larger than others, where trivial solutions are more likely to happen. We next analyze the influence of the number of neurons set in the softmax layer. In previous experiments, the number of classes of dataset is used for setting the softmax layer. However, this number may not always be accessible in real applications. Therefore, we conduct several experiments with different number of k and plot the top 10 samples that have the largest probabilities in each cluster. On NEU dataset, from this figure, we observed that the clustering assignment is done very well when k equals to k real. And the proposed method will bring samples from different classes but with similar pairs together when k smaller than k real. For example, the 3 we used here. Also, as expected, if k is much larger than k real, the textures from same class will the same trend are also present in CFA10 dataset. Here, the k real equals to 10, and another 2 number we used are 5 and 50. In conclusion, a novel image clustering method named self-supervised pairing image clustering was proposed in this paper. It learns clustering from image pairs by an end-to-end pair classification network. For training this network, by excluding any label information, images are formed by a self-supervised pairing module. Besides, since clustering will easily suffer from trivial solutions, 2 additional constraints regularize the training. We applied our method on both manufacturing datasets and the general object dataset, and the result demonstrate that the performance of our method outperforms most of the state-of benchmarks on the used dataset. And that's all.